تمام. Uh, Welcome to all petroleum engineers and students from around the world. And this event that brings together several countries, including Greece, Egypt, Britain, Germany, Yemen, Azerbaijan, and more, in one forum for knowledge exchange and mutual development. Our sixth training lecture today is titled as production optimization. Production optimization. Today's lecture is provided by Mr. Ahmed Al-Jarah. Mr. Ahmed Al-Jarah has more than 12 years of experience in oil and in gas industry, geological study, open hole interpretation, planning and interpretation of production logs, 3D seismic interpretation and modeling. Worked with Halliburton Landmark as a technical sales consultant and with account manager leading Landmark PSL. Currently, we're working at PP British Petroleum as a lead optimizing engineer. We are here thrilled and delighted to have you, Mr. Ahmed Jarrah, and we are grateful for the information that you will provide in this session. Thank you, and you can start screening right now, and you can go ahead.
Thanks a lot, Haider. Do you see my screen?
Yes, I can see your screen. It's clear.
Great. So thank you, Haider, for introduction. Thank you, everyone, for attending this session. So I'm Ahmed Al-Jarah. My current position is lead optimization engineer. So today we are going to talk about the production optimization. What I'm going to presenting here, that will give you a brief of introduction to this topic, which is a quite large topic and has a lot of sub areas and topics. So it's introduction to make you aware about the introduction of optimization and looking into some of the problem, and also make you aware about some method that's regarding the optimization and the availability of the wells and the production petroleum system as well. In the end, I will give you some of the example about the workflow that's currently used, and will sharing some of my experience with you. So I will keep that all the question, and if you have any clarification to the end of the session. So starting with the check my okay, I will starting with this graph. This is actually the asset management in the oil and gas industry. So basically, when we purchase on or we design for any asset, there is the asset potential, and when we have a gap when we install the asset, we have some gap. We losing this from this potential of the asset regarding the installation. It's then we losing some of this potential within the operation range. So within the gap we losing in the installation, it's related to the wrong design or that we select a wrong asset. So within the operation, we losing for some of this potential. So if you see that's the last figure here, this is the actual potential for that asset. It's might be it's losing within the operation, it's we selecting the wrong set point for this asset, or that's it. That will be affecting the installation for asset potential. That will affecting the capex, and that within the operating the actual potential will affecting also the opex. So the studies it's mentioned here in the MENA, in the Middle East and North Africa, for exploration and the production companies operating between 60 to 70% of asset potential. So I am presenting this slide is regarding the asset management because the optimization, in the end of the optimization, we are going to minimize that's the gap that we have in our asset, and we need to minimize the OPEX for that sales.
شلون؟ شو
So, Haider, could you mute the other?
انتوا حتقولون هسه؟
I'm sorry, you can continue.
So this is just a brief, and in general, that's what we have. What's the gap that we have in regarding the asset, and I'm going to start with the production optimization. What is it? Firstly, I want you aware about some of the general terms that we use and how it's handling, how it's used in the industry, and what does it refer to the optimization. So optimization, if we are talking about the mathematical programming or simulation, it means something very specific. But in the oil and gas industry, actually it's involve a lot of activities. All of them can be give that the same outcome and will give you that the same result in the end. I'm going to go through that list. This is the first one is detect the location in the system. If you see here that the petroleum system starting from reservoir ending with the separator. So the first method in the production optimization is detect the location in the system within abnormal high pressure loss and flow restrictions. What does mean that if you see the graph here, it's the pressure loss regarding all the petroleum system. Let me fact out the points. So if you see here, starting with the reservoir pressure, which is the high pressure in the petroleum system, then along with the wellbore, then end with the separator. So this is the pressure drop. That will give you that's the flow rate. So here's it's the graph here is plotted. The graph here it's pressure along with the axis it's the distance. So if you see here that's the pressure drop starting from reservoir ending with the separator. So that is represent the distance between and the pressure drop between the reservoir and separator. So in general petroleum system, as I mentioned, starting from the well ending with the separator or tank. The amount of flow that we can produce from reservoir to the separator or tank is depend on the pressure drop, as you see here in the graph. The pressure drop is between the reservoir pressure here to the separator pressure. So it's depend on the equipment that we install in the wellbore or in the top facilities. The first node that we use in the calculation or in the optimization, that's starting from reservoir pressure. That we can say this is the first node, and with the separator pressure here. If you are going to plot, this will be this is the plot. If you are going to plot the pressure. So what does mean here that the drawdown between that point? For example, that's have the drawdown from reservoir pressure to the wellbore. Then we have tubing loss. Then we have flow line loss, and then finally we reach the separator pressure. Then when we're starting with the optimization, we have to look which part is dominating, where we can reduce this delta P. Another things you need to look for, this is the places that we have abnormal delta P. So if we have abnormal delta P, it's not like this is under like drawdown. If we have abnormal delta P, that's we need to look at this point. It might be we have some problem with this equipment. So maybe close to the separator, or might be it's close to the wellbore or the reservoir. It's depend on that's the problem that we cause that high delta P. So there is some reason it's caused that the high delta P. It might be wrong design for like tubing diameter. For example, if we use like wrong pipe diameter, it's the diameter is too small, then we'll see that's the increase in the diameter and increasing in the delta P, and we have to change this designing, and we have to change this diameter to reduce delta P. Then of some of the components, it's happen typically even where we have in the tubing or flow line, some of the wax, or if we have like a debris, sand debris in the flow line within the time. So that will be see that's increasing the delta P in the flow line area within the time. So in this case, we have to monitor and look at to this curve within the time to see if within the time we have increasing the delta P. That's it might be by like some debrising or wax or any of that debris in the top of the facilities. Or might be we have some of the viscous fluid. This is the viscous fluid is reducing the cross section within the time. So we need to monitor this and see the delta P within the time. If that's increasing, it might be causing that the delta P it's crossing these facilities. Do you have any question?
If you have any question, raise your hand so I can unmute you.
Yeah, I'm like to be that's the interaction in the session. So if you have any question, so don't wait to the end of this lecture. So just you can drop this message in the chat box or raising your hands. So I will continue until, so if you have anything, so Haider, just give me a note.
Well,
So to increase that production rate, we need to look at the whole system. It's not just a one element in the system. We need to look at the whole system. We need to understand also that's the nodal analysis. So I will go with the basic nodal analysis, how we can look at the inflow performance relationship, the outflow performance, and see how we can like increase the production while using the simulation and nodal analysis. So the another method that we use in the production optimization, that's verification of equipment design condition versus the actual operation condition. So for example, if we have like a ESP, electrical submersible pump, that we running in the well, so we need to see that the operating point within the ROR or out the ROR. So you know that the ROR is recommended operating range. That's the companies that we're running, that the ESP is providing that curve. So we can the operating that's our equipment our operating point within the ROR. So this is the figure. This is the example of the ROR for ESP. We have the frequency, the pressure, and the flow rate. So this is the upper thrust and downward thrust. The best efficiency here, we need to operate that our equipment within the best efficiency. So why we need to operate within the phase is it's close to the best efficiency to avoid any of the failures that will happen. Also, that's the efficiency of this equipment. We need to operate at the best efficiency within any equipment. It's not, this is just an example for ESP. So any equipment that's we need to operate within the best efficiency. So if we have a choke, or if we have a gas lift valve, even the separator, so every equipment it's running within that recommended range. We need to operating within the best efficiency.
Mr. Mohammed, there is a question.
Yes.
How to clean debris or wax in the flow line during ESP still running, and the NURS is still also have dirty particles, wax, and debris.
So there is, it depends on the flow assurance study. So you know that's when we start production, we have to do that. The flow assurance study, we need to produce within the range of pressure and the temperature. So if we be out of this range, so will cause that some of flow assurance issues like a wax or something. So to avoid if we face this issue, to avoid this, so we need to just inject some of the chemicals within the pipeline or in the bottom hole if we have like a natural flow, so that will reduce that amount of the wax or any debris.
Yes, you can continue.
Let me know if I just answer your question. So I will go briefly to just explain that the nodal analysis that we use just to evaluate that the performance on the well and do some of that the well simulation or designing some of equipment in the well. So basically we have the reservoir, and this reservoir is connected to the well within the separator, and the pressure data for each node is, let me go to this. Sorry, 1 second. To show you that's the whole system graph. Sorry, back to that one. So we have a pressure, calculated pressure in the reservoir, and we have the separated pressure, which is already calculated, and we have a tubing head pressure, and we have like calculated, or we have a gauge or real-time data. If we have like a DOF, we can calculate it. So all this pressure, it's we know that there's what pressure and production well pressure, and then we can calculate that the IPR. The IPR is the first calculated from the first node from the reservoir pressure, which is the second node in the bottom hole flowing pressure. The first drop, and that's it's called that's inflow relationship. And then when the oil is delivered to the bottom hole of the well, then we need that's the force to deliver the oil to the surface. Then here we can calculate that the outflow performance. It's called like vertical lift performance as well, the VLP. The intersect between the IPR and VLP, which is this is the operating point, the operating point that we're producing on. So the inflow from the reservoir to the bottom hole, it's affected by some of the parameter. So the fluid characteristics, rock properties, and completion design. For the VLP, for vertical lift performance, affected by fluid characteristics and upper completion design. Here is the key parameter is affecting the well productivity in terms of inflow performance and tubing performance. For inflow performance, for sure, this is the reservoir pressure first node is affecting the inflow performance. And as we mentioned before, that's the fluid properties, the hydrocarbon PVT, including the GOR, it's affecting that's the shape of the inflow performance. Water cut permeability, the length of the production interval, so that will affecting the KH. The KH is affecting the inflow performance. The deviation, the well deviation, it's vertical, that's the interaction with the reservoir is less than the deviated well. Well bore diameter affecting the inflow performance. If we have a bigger diameter, so we'll get the better performance. Completion design, it's open hole, it's barefoot well, or case hole. You have casing in the well bore, so that's affecting the inflow. That's affecting the KH and affecting the inflow. If we have a sand control like restriction, that will get the high delta B between the reservoir pressure and bottom hole flank pressure. That will affecting the inflow. The damage is the skin factor. As if we have a mechanical skin, due to that's the drilling operation, or if we have some skin in the or debris that's in the face of in the face sand in the bottom hole, that's will affecting the inflow. Also, the position of the well within the reservoir, if this well in the flanks will get difference like behavior than the well in the flank and in the crest, or in the it's the position on the reservoir. That's all affecting. That's the inflow.
Mr. Muhammad, there is a question.
Yes.
How to calculate operating pressure and flow rate?
I will going to that point in the upcoming slides.
Okay.
And I'm just here is going to mention that's the key parameter affecting the production. So while we do that's the IPR, when we plotting the IPR and calculating the IPR and the VLP, that we need to know what's the parameter affecting our like performance. So if we have the problem within the inflow performance, we know that's we have to know that's the reservoir pressure, the skin factor, deviation. That's the parameter affecting that. We need to adjust that parameter to get the better performance. Even the tubing left performance, we need to know what's the parameter affecting that performance, and after that we can adjust the parameter to get that better shape or better performance. So the tubing performance affecting by like hydrocarbon PVT. So if we have like dense fluids that we need extra like pressure to just lift it to the surface. Water cut and water salinity also affecting, because that's affecting the density of the fluid. the diameter and restriction that we have in the wellbore. So if we have a nipple, if we have a subsurface safety valve, that restriction will affect for sure that's the tubing performance. Even the depth, and deviation, surface roughness for a tubing and casing, that's will get like some of the pressure loss within this surface roughness. Wellhead pressure, if we adjust wellhead pressure, if we like reduce the choke, will get like high wellhead pressure, then affecting the tubing performance. And the last one is the heat loss. So to answer the question, I will show you that the calculation. I don't need to spend some time, but this is the calculation how we can calculate that the inflow performance. We need to look at the last one. This is the pressure. It's mu within H. This is the equation for, where is our mouse? Here is the equation for VLP performance, flowing bottom hole pressure equal to flowing tubing
Mr.
head
Ahmed,
pressure. Yes.
there's no screen.
Sorry, I'm sharing the slides. 1 second. I will share that screen. Do you see my screen?
Yes, we can see it right now.
Okay. So this is the equation for vertical depth performance, flowing bottom hole pressure equal to the flowing tubing head pressure. The tubing head pressure, that's the gauge pressure in the surface. It's equal to the choke, so it's just, which is calculated. So flowing tubing head pressure plus mu and multiply by h. H is the height of the reservoir. Mu, this is the specification of fluid, and plus friction factor. The friction factor, that's we have the pressure loss, it's along the tubing. So this is the equation of vertical depth performance. The equation of inflow performance relationship, that's flowing bottom hole pressure, it's pressure, reservoir pressure minus Q over PI. The PI, which is productivity index.
Mr. Ahmed,
Is it
there
clear?
is a question. How can we calculate the outflow performance without using a software?
This is the equation of outflow performance, the inflow and outflow without using software. So this is the example, hands-on example. I just given that the rate. So you know that every well we have a well test for every well. The well test is give us the rate and the tubing head pressure. So the tubing head pressure is, we know the tubing head pressure, we know the rate, and we know that the friction from that's the tubing manufacturer. Then we can calculate based on the equation, we can calculate the pressure drop. So flowing bottom hole pressure for if you see here for 30 psi, then we can use flowing tubing head pressure, which is 30 bar here, plus the mu of that the fluid, which is 0.1, multiplied by height 1,000 meter, the height of the well, plus the friction factor, which is already known. So then within the every rate that we have to calculate this, then we have to plot it on that rate, on that graph rate within a pressure. The pressure here is the first node. It's if we have like 0 rate, the bottom hole flowing pressure is equal to the reservoir pressure. Here's the first point, it's reservoir pressure. Then we have a drop in the bottom hole flowing pressure. When we start producing, when we get high rate, then we will get a drop. So we have like 3-4 points based on the rates that we have here. Then we can connect this point. We'll see that this is the inflow performance. Then the outflow performance, the same equation here. Is it clear? Tell me if it's clear. I can move to the another topic.
It is clear.
Okay, great. So here, that's the figures here. It's showing that's the effect of the tubing size on the inflow performance and outflow performance. So if you get like a bigger tubing size, so we'll get the higher rate based on this figure. Then if you see here that the affecting with the tubing size on the inflow performance and outflow performance as well. Same, this is the affecting tubing size. As if you have like the IPR here, then while we increasing the diameter of the tubing size, so we will get the better production. So, but I will show you here. This is the maximum. This is how we calculate the optimum tubing size based on that based on the well. So if we get like bigger a tubing size, we'll get like better production. Then we reach this point, so the bigger tubing size will not affect that will not get any effect on the outflow performance. So this is how we can calculate the optimum tubing size. This is the rate with the diameter, and then we will, when we reach this point, we'll get that the optimum. If we get like, if we choose bigger than this one, so we'll move to the unstable region. So also from the shape of the outflow performance, so we can like give you an indicate of the problem that we have, the issue that we have in the world. So if you see this shape of outflow, it will give you the indicate that we have like tubing, it's too small in the bottom hole. So we need that's we have a wrong design. We need to redesign the tubing size. Even that the shape of the IPR is give you that indicate that we have a restriction by inflow. So it's might we have like a skin, we need to stem that swell, we need to reduce that skin. So the density of perforation is affecting that inflow because it's increasing, like that's increasing that the permeability and decreasing the skin factor in the wellbore. So the same with the how to choose that the optimum diameter. So here's the rate along with that the number of perforations that we choose. So this is from this graph we can choose based on our wells, our reservoir, that we can use the optimum numbers of perforation that we fit with our reservoir to give you. That's the high performance with the inflow performance on the inflow performance relationship curve. So this is the graph is showing how it's the effect of perforation density on inflow. When we're increasing the numbers of perforation, that will give you that's a better performance than we reach that the optimum points. Any increasing of numbers of perforation after these points, so will not give you any effect. So back to the optimization like approach optimization workflows. So this is I will go within the most workflow that we use in the oil and gas industry, and currently we are using this workflow. So identification and addressing a flow that have disadvantage that we don't need like to flow that's fluid, like a high water cut, high H2S contain, and we have to do something about it. So if we have like constant rain and we need to reduce the production from those well, so if we have like a H2S constant rain, we cannot handle it on the facilities, or if we have high water cut wells and we don't have any like water handling facility on the surface, so we have to reduce the production from those wells. So then that's will allows you to increase that production from the another wells. So here it's identify and correct system manufacture and unwanted behavior. So the failure is distribute the production, shut down your plan. It's when we have a poorly set point and affecting our production, that will give you alarm and it's cause to shut some wells and it's difficult to back it online. So in this case, we need to just to see that's why we get that alarm, why that alarm happened, and try to address the reason. Is it poorly set point, or might we have to change some of the equipment in the borehole or in the surface? So here's also within the production optimization approach. So analyzing and improving logistic and planning for maintenance or replacing and installation the equipment in the execution field activity. So if one of the equipment breaks down and we don't have the parts in the storage, then we have to wait a long time for these parts to come. So even when you want to add some of the components, so there is a room of the optimization uh, or affecting that component. So in this case, so we have to optimize when we need this equipment, when we have to start do maintenance for that well for any intervention in the wellbore. So to reduce that the downtime of the production, then we will get that the logistic optimization in this point. So this is the new term in the oil and gas industry, reviewing that the occurrence of the failures and recognize the pattern. So it's related to the data analytics, the data science, some of the machine learning algorithm using. So now we have working on that some of the project. It's ESP projects, trying to collect some of the failure data in that ESPs and trying to find some pattern on that data. To do some of the workflow and optimization workflow based on that result. So this is a new terms in the oil and gas industry, working on the data and data analytics, data science. It's also, this is part of the optimization steps. So the another part of the optimization, calibration of instrumentation. So the calibration, so actually we trust that the value that's come of the instrument. Obtaining system rate or certain pressure, but that instrument can be often not calibrated. It might give you a wrong reading. So we have to do some of the calibration of our equipments. Identification of operational constraints, like for example, it's water handling capacity or power capacity. So in this case, we have to identify that the bottlenecks that we have and restriction we have in the production. The constraint, like addressing the constraint, allow you to recognize some of the bottleneck. So you might face when you're designing for future. So for example, mm, I like to give an example with the ESP wells, because you know that's now it's moving from the natural flow to the ESP. Most of the well, it's we need some of the lifting method just to produce. And like for example, here it's if you have the plan to run some of the new ESP, and we need some of power, so we have to aware about how much the power that we have when we're running this ESPs. So this is the part of the optimization, identify the capacity, water handling. So we have to run our simulation to see what's the water production, and we need to update and upgrade the facilities is to handling that water capacity, even the power capacity or any future design that we have. So we need to identify that operational constraint to just avoid any of the constraint in the future. So find control setting of equipment or system characteristics that give you production, the higher production rate than the current. So this is, so if you have some of the behavior in the one well and trying to see that's the effect of this behavior. So for example, if you have like a producer where it's surrounded by injector wells, to see that some of the behavior of that injector, it's around that a producer, So we have to do some of the measurement in that injector to see that's the effect of the injector within that effect on the producer wells, like running a PLT within the injector wells and within the producer, see that's the production profile and comparing to see what's the impact. It's if there's any impact or there is no impact at all. So it's defining the control setting of the equipment or system characteristics and give the production higher than the current. This is the right definition of the production optimization. It's in the industry. Oh, so we have to identify the bottlenecks that we have. This is the most common and workflow and related to the optimization in the industry. Even that we have to identify the monitoring key performance indicator. This is very important. So it might be that we need to maximize the revenue we have, like to, if you need to maximize the revenue, we have to increase the production rate. But if we need like to minimize the water rate, so if we don't have any like water handling facilities, we need to just reducing that the production. It's along that's the wells that producing high water cut. The key performance indicator is depend on the constraint that we have, depend on the plan for the operator, the field operator. We have to identify the key performance rate indicator. So all these step is actually it's using in the oil and gas industry. It's under the umbrella of the production optimization. This is the most common. It's a step we are using right now. It's finding the control setting for the equipment and finding the control setting and identify that's the KPIs based on the KPIs. So just selecting the set point based on the KPIs that we have in the company. Any question till here?
Yes, there is a question in the chat box saying, are there any effective tasks for erupt if wells optimization? That's the question. I didn't understand it, so I told him to rewrite it.
Yeah, could you elaborate more?
Yeah, I will ask him to rewrite it.
So if you can like just unmute yourself and ask the question, that will be better. Let me see.
Hello, Mr. Ahmed Al-Jarah.
Yes.
Sir, I'm asking, thank you for this information. I'm asking about the wells, eruptive wells. So when we don't need to gas lift or ESP pumps, what's the actions, effective actions to do in order to optimize this kind of wells?
So we need to redesign in this kind of well. We need to redesign that. Starting with the inflow to the outflow. So we need to see that we have any restriction. If we have any of the going to the ID of the tubing size, or if we can changing the choke on the surface. This is the task that we can use to increase the performance of this well. If we cannot, so we need to something to lift that the fluid from bottom hole to the surface.
Thank you, Mr. Ahmed. Thank you.
Thanks, appreciate. Any question?
You can continue, Mr. Ahmed. There's
Okay,
no question.
thanks. Let's move. So what's I just showing that's the calculation, the hands-on calculation. So when we do the optimization, we need to build the model. We need to build that model based on the physical model. Then we can optimize. We can running the optimization based on that. So when we need to build the physical system, so we have to have the control variables, and then building the physical system, then we will get the measured variables here. Then the model parameter here, we can adjust it to get that the model of the physical system. It's give you that the model output variables is different than the measured variables. So this is the simulation loop. Then we can optimize to change that the model parameter. Then will give you this optimization loop based on that the control variables and model parameter. So model parameter, it's like a PVT that's the rock properties that we have, any of the fluid or rock characteristics that we shown affecting on our model. The control variables, it's the choke size that we have, the tubing size, casing size. This is the controls variables that we can control our rate with it. So actually we are using some of the software to do some of the well the control variables that we use: well replacement, well rate, and well status and well routing. So if we change a well routing based on the different separator pressure, so that will get like different performance on the well. or designing for ICD inflow control device or inflow control valve to get that better profile, production profile, and reducing the water cut. For mid-term, so we maximize the oil production in the mid-term, and the way we maximize the oil production, how allocation, scarce resources, water injection, and power. The variables that we use, as I mentioned before, choke opening, adjusting the choke, water rate, pump frequency. If we have like ESP, changing with the pump frequency, increasing the pump frequency will give you the maximum production from that well within this is the pump, even the well routing. For short term, maximum the production revenue with the short term, reduce and mitigate that fluctuation, the variables that we have, control valve opening, water injection rate, and pump frequency. This is most of that the method that we use in the optimization, the introduction. As I mentioned, this is a large topics with the large sub areas topics as well. So I just give you that's the introduction of that. So this is a course for 3 days. I cannot handle within 1 hour. So just let me know if you have any question till this slides. We have to end this lecture. So now it's free to ask any question.
You can write your question in the chat box, or you can raise your hand so I can unmute you.
Yes, Mark.
Mr. Mark, you can unmute yourself. Mr. Mark, you can go ahead. There's no...
We can't hear you, Mark. Your voice is fluctuating.
There's a problem with your mic, Mr. Mark. Try to write your question in the chat box and I'll read it to Mr. Ahmed.
So basically we have like 3 stage of optimization that we are working on it right now. So the production add. So when we optimize the choke or optimize the frequency or changing the design, so that's any action that we have to do to add any rate. So this is the under of rating add of one of this optimization stage. The second stage, it's rate recovery. So when we get like when we have to set the target for each well, and for some reason the well it's like operating out of this target and above this target or below. So we need to back this well to the target. Like we set the choke size and frequency for that well, and if we have like a genset issue, power issue, we have to reduce the frequency of that ESP that's will affecting our production. So then we have to back this well to the target. So This is under the rate recovery stage. The third stage, it's protecting the well. It's the optimization. It's not mean that's increasing the production. Sometimes the optimization is reducing the production to protect the well or protect the reservoir. So when we're reaching the bubble point, so we have to choke back that well. So we'll lose some of the production, but we are protecting the reservoir. This is part of the optimization. Just we need, so just I need to send this message. The production optimization is not just meaning that increasing the production rate. Optimization sometimes it's reducing the production rates to protect our equipment or protect our reservoir. Yes, if you have any question.
If anyone does not have any question, we have reached the end of this session. We would like to thank Ahmed Al-Jarah, Mr. Ahmed Al-Jarah, for this great and very informative session. Uh, uh, we are grateful for you, Mr. Ahmed, and we hope you a good night and a great future, I guess. So thank you for this information, and we hope and we are grateful for you and for accepting the invitation. Thank you, Mr. Ahmed.
Thank you, everyone, for attending this session, and all the best for you all. Thank you.
Thank you, Mr. Ahmed. Thank you.
Bye. Take care.
Please, everyone, you can register your attend via the link in the chat.
Please, everyone, register your attendance through the link in the chat box.